I'm making this video because I would caution the engineering student who is studying thermodynamics and energy systems and the first law, energy balance, to not get overwhelmed by the process. Even though it seems difficult that we have this first law energy balance, all the energy in, all the energy out of a system, and we have so many units, we have so many terms in our expression, it really, for lack of a better pun, boils down to, most of the constants, most of the terms cancel out, and we have like a small section of the thermodynamic picture to deal with. So I want to do some, I don't want to say easier problems, but some problems that are easy to overthink. But I want to show you how simple the solution is. So here we have a steady flow device. A steady flow device means, it's something like a pipe, maybe. Our boundary looks like this. We have flow going in at m dot, and the same flow must come out at m dot in kilograms per second flow rate. So that's what steady flow means. We have an m dot, we have yes flow, has a density of given density, and this many meters cubed per minute, that's volume over time, entered in, and determine the mass flow rate if the exit area is this. So the area at the exit, here's the entrance A1 and A2 is even given. And assume density is constant. All this is our equation for what is mass flow rate. Well, mass flow rate is by definition our density times, our mass flow rate is our density times our volumetric flow rate. Let's remember that Q is volumetric flow rate. It's the amount of volume, meters cubed per second. And we are given that here, right? In meters cubed per minute. And density is constant. And what fluid did I say? I didn't say fluid here. Let's assume that it is water. And then this is all we do, 1,000 for water, and that would be kilograms per meters cubed, times the flow rate, which is 2,000 meters cubed per minute. So the flow rate ends up being 2.0 times 10 to the 6. And I can leave that in kilograms if I want, per minute, or I can put that into kilograms per second if I want to by just converting those units. So don't overthink a problem like this. And then fluid enter a steady flow device has a density, because this is sort of looking at our, like, don't forget when you're working with thermodynamics that you also, have to have your knowledge of your fluids, right? Fluids is your flow rate, your continuity equation, Q equals mv, your velocity of how that fluid works. It's mass flow rate, its density, it's weight per unit volume, et cetera. It's mass per unit volume, et cetera. So we have to remember a bit about fluids in order to do thermodynamics, but it's not necessarily difficult. Let's look at this one. Fluid is entering a steady flow device. Oh, and I did assume density here. So it is water. So here we go. We have water again. If it's a steady flow device, let's see. Exit velocity, exit area is known. I don't know the inlet area here, but there is flow. I can set a boundary right here in the middle of it. It's going to flow in and back out again. And we want to know the exit velocity, V2. Well, here we were given the density. We're given the volumetric flow rate in meters cubed per minute again. And I know the continuity equation, Q equals AV. If you don't know the continuity equation, please ask me and I will absolutely update, make a video on what that is if I don't already have one in the playlist. So Q equals AV, classic continuity equation. It just relates the area that a fluid is going through, and a volumetric flow rate needs to go through that area. 2,000 literally meters cubed that take up that much meters cubed have to go through it in 1 minute. So in order for it to go through it, it depends on the velocity. And in order for 2,000 meters cubed to go through this area in each minute, of course, we can calculate how fast it should be going. It would be going 2,000 meters cubed per minute over 0.5 meters squared, which is going to give me 4,000, one significant digit, meters cubed in a minute. No, not meters cubed, meters. Of course, meters cubed and meters squared. And of course, I want meters per minute because this is a velocity V2. I didn't even care what V1 is because I was given Q. I didn't have to calculate it from V1. Okay, now let's look at one that usually raises a little bit more anxiety. This one is a steam turbine. It has an inlet flow of this amount of mass per hour. So that's a mass flow, right? Has a specific volume. Specific volume is 1 over density. The inlet diameter is given and outlet diameter is given. That means I can calculate A2 and A1. If the outlet volume is 0.1 meters cubed per kilogram, determine the inlet velocity. Here, I would want to kind of draw a steam turbine. We like drawing steam turbines like this. And I don't really know everything about this, but I do know it has an inlet and outlet. I do know that mass is flowing in there at a velocity V1, ending at a velocity V2. I know that it's going to be putting work in that system. I know it might be losing heat, etc. But I don't necessarily need to know all of these things. And I don't need to use the entire first law energy balance. I can just, I can recognize that what matters here is my velocity, and I can relate my mass flow rate to the velocity all at the inlet. So I have a mass flow rate at the inlet. I have a specific volume, so a density at the inlet. I have an area at the inlet. I don't think I even need it at the outlet. So I can relate these things. And if I'm intelligent about it, I can just use my continuity equation and break up my continuity equation into mass flow rate times specific volume and realize that at the inlet area A1, this will be my relationship. So don't overthink it. Don't use an entire first law energy balance if you don't need to, is my point. So this will be A1 times velocity over volumetric or specific volume, which is 1 over density. Alternatively, you might have seen this equation with a density in the numerator. Of course, the area is then going to be pi r squared. 0.05 meters squared. And the velocity is the velocity. Is that what we're solving for? Yes. Inlet velocity, we're solving for inlet velocity V1, and our mass flow rate is 100,000 kilograms per hour. And volumetric or specific volume is 0.05 meters cubed per second. Make sure that you keep these units, kilogram per hour, meter squared, meter cubed per second. Work that all out and you will find that you will get yourself velocity at the inlet equals 176.9. And I think we only have one significant digit in this problem, two significant, yeah, really just one significant digit. But I'm going to go for two significant digits, 180 meters per second is the answer to this problem. I didn't overthink it. I didn't use the first law of energy balance. I just used my knowledge of fluids and thermodynamics collectively to solve that problem. Here's another one. It's the same question, same variables, but this one says, what is the outlet velocity? Well, I'm going to do the same thing. Q equals m dot v. Q equals m dot v2. And I know m dot and I know, let me see, outlet volume, here we go. Meters cubed per kilogram. Kilograms cross out, meters cubed per hour, I get. And if I don't want an hour, then I put it in the numerator here so it can cross out. And I say there's 60 seconds. Oops, not 60 seconds, 3,600 seconds in 1 hour. So I get 2.77 meters cubed per second is my volumetric flow rate at the outlet. Well, it should be the same at the inlet as well, unless it's a compressible fluid. So now from this relationship, I'm just going to use Q equals AV. And I know what Q is. And what am I trying to solve for here? V2. So Q2 equals A2 times V2, but Q1 equals Q2 we recognize, and I probably being given A2. So then my volume at V2 is going to be Q over A, which is 2.77 meters cubed per second over 0. Where do I have the area? Let's see, area. I had to calculate it. So the area 2, A2, don't like doing math over here. Actually, I'm not going to do it over here. I'm going to do it right in the problem. A2 is down here, so that's going to be pi times 0.1 squared meters squared. This is going to give me in meters per second. Hopefully that's what I want. Yes, velocity should be in meters per second. And if I work all of that out, I'm going to get 88.46 meters per second. Quickly look at my significant digits in the problem. Really, it's just one significant digit. Let me keep two so that I don't stress you out so much. Meters per second. And that, again, I just want to demonstrate that, yes, this is a thermodynamics problem, but because of our knowledge of fluids, it's not really a cumbersome first law energy balance problem. Let's do another quick problem. Fluid flows past a section of pipe. Section of pipe should define a boundary. It's a flow problem. Mass flow rate. Mass flow rate. It has a pressure. Pressure equals 100 kilopascals. And has a specific volume. Remember, specific volume is 1 over density. Determine its flow work. Ooh, flow work. We have to remember what flow work is. Work is pressure times volume. That is flow work. It is the number of joules that are done per second. Remember, work is energy over time. And this is the number of joules per second that happens when things are pressurized or depressurized. So that's the only equation that I use here. And I think I'm given the pascals, and I am given the volumetric flow rate of 0.001 meters cubed per kilogram. And if you take the time to convert your pascals, then you're going to get your 100 joules per kilogram. Sorry, it's not per second, it's per kilogram. The flow work that is being done is the number of joules per kilogram of flow that flowed through at a certain specific volume. So it's just 100 joules were done by each kilogram of flow. So therefore, 100 joules of energy did work per kilogram. And if you want to do that in a rate of time, you could divide that per second just by multiplying it by 1 if you want to, if you want seconds in the denominator there. So again, a question that you really don't want to overthink, and make sure that you use your fluids knowledge, use your thermodynamics knowledge, and not every thermodynamics problem is difficult. Thanks for listening.